Great. Welcome back to our second to the last seminar of before the summer. This is the Galaxy Science Interest Group of the NASA Cosmic Origins Program. Today, we're going to hear from Rebecca. So thank you all for coming. And Rebecca, I'm not gonna do boring introduction. So instead, I'm going to ask you two questions and have you introduce yourself. So first, I'm going to ask you to tell us a bit about your career path. Where have you been and where are you now?
So I originally joined the military out of high school, and so I was an Arabic translator in the military, and then I went to college afterwards. I was a business major for a while, and then ended up in astronomy by accident at UT Austin in Texas. And then I stayed there for graduate school. I did a postdoc for a few years at RIT in Rochester, New York, and I am now the Giacconi Postdoc Fellow at the Space Telescope Science Institute in Baltimore.
Great. We're actually colleagues. So I couldn't do the introduction myself.
Mhm.
Okay, so the next question is, when was your first exposure to what you do now? And have you always been working on the same thing?
So I have not always been working on the same thing, actually. In undergrad, I did a research project on turbulence in the ISM around stars, and if there was actual observational evidence. And we discovered that there was observational proof of turbulence in the ISM, which was a really cool project that I got to be the lead of. And then I applied for graduate school, and I got in at UT Austin working with Steve Finkelstein, and he does a lot of reionization era, high redshift, early galaxies in the early universe. And I think in my interview process, I said, make me care about what you do. And he did a pretty good job because I'm still doing these high redshift, very distant early universe galaxies.
Nice.
Mm-hmm.
Great. And I can't wait to hear about your research. So you can go ahead and share your slides.
Sure.
So today, Rebecca is going to tell us about advancement in exploring the early universe, unlocking the mysteries of galaxies during the reionization era. So take it away, Rebecca.
All right, thanks, Aaron. Yeah, so like Aaron said, I'm going to talk a little bit about exploring the early universe. And kind of what I want to start off with is, what do I mean by the reionization era? Or when I say high redshift galaxies, what redshift am I talking about? And so I like to show this particular graphic, even though I know there's a lot more updated ones, where we see here at the bottom is redshift going in from left to right, or we have time since the Big Bang going from right to left. So it's kind of a little bit of an illustration of the history of the universe and how far back in time we could see with ground-based observatories, and then with Hubble and the Hubble Deep Field, and then when we got Hubble infrared, we were able to push back into the first billion years after the Big Bang, and just kind of barely able to see some of these early galaxies with the Hubble Space Telescope when we got infrared capabilities. And then with it said future JWST observations, we would be able to reach back to like the first 500 million years. And I like to slap a nice current on there because I still can't get over all of the advancements that we've made with JWST in the last few years. So what I want to talk a little bit about to begin with is where we came from and how do we get these early galaxies and how do we study them. And so one of the best ways I found to visualize this is from this video that was made showing how the actual spectrum of a galaxy changes at different redshifts. And so the gray shaded region that you see kind of shifting across the screen towards the right is a spectrum of a galaxy. This is the light emitted by a galaxy as you go at higher and higher redshifts or early and earlier on in the universe. And these are the Hubble filters, for example, showing how the actual images at the bottom correspond to each of those filters that you see at the top. And so you can see a galaxy at redshift 3, and some change is actually visible at all of these different wavelengths because the light is emitted that way. But as you shift to higher and higher redshift, you drop out of these images. And so when you get to redshift 8 or 9, you only have 2 or 3 actual images of this galaxy from Hubble. And so trying to study these early galaxies with HST or the Hubble Space Telescope earlier on was a little difficult. You only had 3 data points to go off of, and oftentimes trying to fit data to only a few data points is difficult, especially when other things could show up that look similar to just a few images of certain galaxy. It could be something that's lower redshift and redder, but it could be something that's high redshift, or it could be some kind of artifact in the data if you only have one data point. So we were only able to look so far back in the universe because we needed to have multiple images to detect these sources. And so that's what we did. Here I'm showing actually the Hubble ACS and with C3, so the Advanced Camera for Surveys and Wide Field Camera 3, and the infrared images here under the blue. And so these are actual Hubble images of some of these early galaxies. And so these sources were all expected to be between like redshift 8 and 10. And so you can see that they're shown in these last three filters in HST. And we also had Spitzer, which was a beautiful kind of trash can of a telescope, where it actually is we're operating in the infrared. So we do have infrared images of these galaxies. So in the longer wavelengths where there's still more light, you actually do get some images, but the resolution, as you can see, is a little bit lower than that of HST. And we were struggling with the blending sources that were nearby and things like that. And so we do have some pretty clear images of a couple of these sources, but a lot of the times we're dealing with contamination from nearby objects because of the low resolution of Spitzer. So this is what we had prior to JWST. This is how we were looking for these high redshift galaxies. And we would identify them in imaging, but we want to actually get a spectrum of the source to get a spectroscopic redshift. And so in order to do that, you would use spectroscopy, and largely what the options were from the ground to use 6 to 10 meter class telescopes like Keck, which we're showing here. So this is a simulated spectrum of a galaxy. This is what the spectrum of a galaxy looks like, whereas that shaded region before didn't have any of the emission line features on it. This includes some of the emission line features you would expect from a galaxy, and this is a simulated galaxy at redshift 7.5. And so what you see is on the right-hand side, we show the filters for Spitzer. So these are the filters that Spitzer was observing in. So these would be imaging. And then you have some of the imaging filters in green from HST. So these are the images that you're seeing. Here's like the very blue end. So this would be like the more the image before they would drop out. But what you can actually see is there's an emission line here. This is called Lyman alpha. And so for observations with the Keck telescope, which are shown in blue are these Keck filters, we would be able to detect this Lyman alpha emission line from these galaxies. All of the rest of these would be invisible to our spectroscopy because, as you can see, Keck only goes to this wavelength, and the brightest line that you can see at these redshifts at these wavelengths is going to be Lyman alpha. Now, unfortunately, Lyman alpha is difficult to study in the early universe because of this reionization process. So at some point, all of the material in between galaxies was neutral hydrogen, which absorbed all of the light blueward of a certain wavelength. And so you can see that here on the right-hand side with all the white is all opaque to this light. What you need is some sort of reionization or radiation that can reionize or ionize this hydrogen and ionize all of the medium in between these galaxies such that this light can now travel through and get to our telescopes. We think this happens in regions that are overdense, meaning there's lots of galaxies like this big blob here at the bottom, where we have a big galaxy, but a lot of small galaxies contributing to making a bubble large enough such that this Lyman alpha light can escape and get through this neutral hydrogen and get to our telescopes. So not only are we only able to see a single emission line from the ground prior to JWST at these wavelengths, but it's also a very difficult one to detect because it requires these galaxies to be in this particular scenario and not in something like this. And so we could tell a lot about reionization just from detecting Lyman alpha from these galaxies, but we also needed to get redshifts. And so it was a difficult thing to do. This is where Keck came in, like I said before. So we actually had a record-breaking galaxy from the ground, which was at redshift 7 and change from Steve in 2013, which was easily broken a few years later. And so this observatory was able to do a lot of really good science. We were able to detect, these are some examples of some Lyman alpha emission. And here was the record-breaking Lyman alpha spectroscopic redshift in the Hubble era from Keck. So this was redshift 8.68. I just want to point this one out here from Adi Zitrin, where they had this Lyman alpha detection at this redshift here. And so this was as far as we could go, with the instrumentation and the telescopes that we had prior to JWST. And this is, again, affected a lot by, absorption from the atmosphere. And so you get a lot of skylines kind of in the way. And so you have to be pretty lucky to get some of this, as well as, being in particular environments in the universe for these Lyman alpha lines to actually get to you. And so when we tried to do this, I tried to do this at redshift 8 and 9. And so I had a program called the Islands of Reionization program. This was during my PhD on the Keck Observatory, where we were targeting a lot of the candles extragalactic fields. So these surveys that were studying deep imaging of a lot of different spots on the sky. And we actually were able to found a Lyman alpha emission. So we found Lyman alpha from a galaxy at redshift 8.6, which was really exciting. It worked. We were able to actually get a Lyman alpha emission. But interestingly enough, it was actually close to this other one that I showed you before. And so it's possible that there's an overdensity of galaxies here at this redshift, which could explain, like I said before, why we are seeing Lyman alpha from these particular sources is because they're in an overdense region. And so this was a pretty exciting project. But what else could we do in the Hubble era? Sorry. We also have here, I'm just kind of showing the record holding galaxies from HST. So this was the previous record holder, which was this Lyman alpha line I showed you from Keck at redshift 8.68. And then a source that you might have heard of called GNZ11 had a spectroscopic redshift from Hubble, from the GRISM, from the break. And that was at redshift 11 or so. And so these were as far as we could go. And these were kind of the two highest redshift sources that we had spectroscopically confirmed prior to JWST. We had a lot of other target galaxies, like candidate high redshift galaxies, but none that were confirmed. And so preparing for JWST, I also wanted to just do a quick shout out to some templates that we made. So early galaxies are going to be bluer, they're going to be younger, they're going to have higher ionization, lower metallicity, and that kind of changes what the spectrum of the galaxies look like. And so in order to prepare for some of these observations and to use better templates to fit the photometry, the imaging that we were getting, we came up with some templates that we've published. So Dr. Taylor Hutchison and I put this together. If you're interested or if you have observations of early galaxies and you are finding that you're not getting good redshifts, perhaps try using some of these templates that are more catered to the type of sources that we expect these early galaxies to be. You could find that there at the QR code. So then we were kind of ready for JWST observations to start. I like to show this picture. It's just a telescope alignment image. And so this was very short exposures. This was just to make sure that the mirrors were all lined up and that we were getting stars that looked like point sources with the dispersion of the actual telescope optics. But in the background is actual galaxies. This telescope is so incredibly sensitive. It's so much better and so much more sensitive. It's so much more resolved than everything that we kind of expected it to be. And so like we can do a lot of really incredible science. And I freaked out a little bit about this image because of the galaxies in the background that you're able to just see in such a short exposure time. This telescope is truly an incredible instrument. And what did we do with it? So one of the first things that we did with JWST is we pointed at a lot of these galaxies that we had known about with HST. And so we had our imaging in the candles fields. These were like surveys of certain spots of the sky that had a lot of deep imaging. And so again, I'm showing those same images here at the top. Here's the blue from HST. And then over here on the right is the red from Spitzer. And so this is a particular object. In fact, this is the one that has the spectroscopic redshift redshift 8.6. And so this is the imaging we had before, and then to try to put it into the right order and put them where they fall in the actual spectrum. We have the images from the Sears survey, which was one of the first early release science surveys of these sources. So not only did we gain more data points for our model fitting, but we also gained resolution. And so we actually have really good detections and higher resolution of these sources that we're able to use. So instead of having all of this blurry imaging from Spitzer, we have really well resolved and detected infrared imaging of these sources from NIRCam. So this is pretty exciting. We can study galaxies even further away, but we can also study these galaxies that we were looking with Hubble and try to confirm that they were actually the sources we expected. And like I said, we had improved sensitivity, but we also have improved resolution. And so I'd like to show this is the Spitzer IRAC image. This is the color image of the Spitzer IRAC filters. So the shorter wavelengths of Spitzer, and then on the right-hand side is the longer wavelengths with Spitzer MIPS, so 24 microns. And so you can see that we had a lot of detections in Spitzer data, but they are a little bit blurry. They are low resolution. And so not only do we get increased sensitivity, you can see fainter things in the JWST MIRI imaging than we could see with Spitzer, but you have improved resolution. So you actually can resolve out these individual sources right here and see a lot of the fainter things. So JWST truly was able to do a lot with the NIRCam and the MIRI instruments for imaging. And one of the things that we were able to do, like I said, was have improved resolution. And so here I'd like to show one of the highest redshift candidate galaxies that we had with HST. So this is from the Cosmic Springs program with JWST, but this was a source that was discovered in 2012 by Danko. And it had a photometric redshift here of redshift 10.7. This is a lensed source. So using the power of gravitational lensing and the multiple imaging that we get for this particular source from this cluster, we had this like little red blob here that we had a photometric redshift of 10.7. So again, one of the first things we did early on with JWST is point our imaging at the images are at the locations we had HST imaging. And so here you can see this is the NIRCam imaging of the same cluster, and you still get the same three mirror images of this source. But we find that it's actually not just one source. You can actually resolve that it's two interacting galaxies at a redshift of still 10.6. So our photometric redshift still indicates that this is a high redshift source, but it's actually two interacting galaxies, which could be why it's so bright. It's triggering some star formation and things like that. So the improved resolution of JWST really kind of opens up this early universe study and understanding kind of the galaxies and how they interact, what their environments are, and other things like that. Like I mentioned before, one of the first observations we had was from the SEERS program. So this is an image from NIRCam of the SEERS observations. And so this was a pretty exciting program to be part of. It was one of the early release science programs. So the first day that data came down from the telescope publicly, we got our imaging data. And so one of the first things that I did was look at all the pretty pictures. And you can do this by looking at, you can download these images if you'd like to zoom through them. We picked out a couple objects that were quite interesting. The first supernova that was discovered with JWST is here. This little dot is actually a supernova that was discovered in the SEERS imaging. And we've shown some other really cool details that you can see in these spiral galaxies. I like to call this one Pac-Man because it looked like Pac-Man to me. And we nicknamed this one the Space Kraken for reasons that were probably obvious. But this was just a lot of fun to kind of get to see these galaxies in such great detail and just to zoom in on some of these images. So I encourage you to do so. And the link is right there if you'd like to take a look at it. Again, what we really wanted to do with JWST is just look for more distant galaxies, right? We have longer wavelength coverage, so you are able to look at higher redshift sources. And one of the first things that we found with JWST was a source that was at a photometric redshift of 12. So this was further, as far back as we expected we'd be able to see with these images. And so this was really exciting. In fact, we found this object in the SEERS team, in the SEERS data, on P.I. Finkelstein's daughter Maisie's birthday. And so we actually ended up naming it Maisie's Galaxy after her, and she was very excited. It was a really great birthday present. We were able to put this paper out on our discovery of this galaxy at redshift 12. And because this data was public, we had a lot of other people that were looking at the data. In fact, the entire of the high redshift community was really excited, and we got to provide all this fun science for everyone to do. And on the same day that we came out with Maisie's Galaxy, another team came out with some potentially high redshift 16 galaxies. And so we actually didn't even think to look that high. When we were looking for Maisie's Galaxy, we kind of did our cutoff at redshift 15. So we missed this in our initial searches. And so it was potentially a redshift 16 galaxy. But like I mentioned before, because you only have so many data points when you're looking at these high redshifts and you're pushing the boundary now to like NIRCam's limit, we only have a few data points here, and you can see those in red circles here. We only had 5 data points to do this with. It looks like this break for this black spectrum right here, it looks like it's a high redshift or redshift 16 source with a break right here. But it could also potentially be a low redshift source that's a little bit red. And so with these strong emission lines, it could actually mimic this break in the spectrum that looks like a high redshift galaxy. Similarly, Jorge Zavala also had a paper out on a source that could have been redshift 13 or could have been redshift 5, but in this particular case, we had the longer wavelength data. And so we had the submillimeter data to actually look at this and put some constraints. And so we could rule out the high redshift case, right? So this was actually a redshift 5 source, we said, instead of redshift 13, because we had this ancillary data to take a look at it. And so it's pretty exciting that all of these programs are coming out with data. We're finding really exciting, even higher redshift sources. And we're also finding things that are surprising and weird. And we're confusing ourselves on top of everything that was going on. We were finding that we needed better models of things, even more than we had before. And so I just wanted to bring this particular spectrum back because I think it's quite striking. So we have marked out here where we could see with this the telescopes that we had prior to JWST. So from the ground, from Keck in particular, in this case, we could see about up to here at redshift 7.5. And then the rest of this was completely unreachable. But at redshift 7.5, JWST's near spec can cover this entire wavelength range. And so not only could we detect these galaxies in our images and confirm their candidacy as high redshift galaxies, but we can discover high redshift galaxies with JWST. We can also follow them up and confirm these galaxies. So that's what we wanted to do as well. So we had spectroscopy of these early galaxies with the SEERS program as well. And so what I'm showing you now is not a simulated spectrum. It is a real spectrum from JWST's near spec. And this is, again, less than an hour of integration time in 3 filters with JWST near spec. And you can see all of these really strong, really exciting emission line features. You can study the detailed composition of these galaxies, whereas before with Keck, all we could really see was about right here, which was just this Lyman alpha line, which this is the actual redshift 8.7 source I showed you before that had Lyman alpha detection. And so this was the only sensitivity we had prior to JWST. And now we actually have opened up these galaxies to true detailed studies, which was really exciting. And as well, this is the spectrum of GNZ11 from JWST near spec from the JADES team. I cried when I saw this paper come out because this is an insane looking spectrum. This galaxy is super bright, super weird, but also the detail that you can get out of the lowest resolution on JWST is just phenomenal. And so just to remind ourselves, this is what we saw with HST, the GRISM. We saw this little break right here. And so we had no other information about this galaxy or its composition or anything about it prior to just having a spectroscopic redshift. And we find that it's actually a redshift of 10.6 because this turnover here is not quite as sharp as we expected. And so we still have a high redshift galaxy. This is still one of the more distant galaxies that we've studied. And so this was actually pretty exciting coming out of the JADES team really early on. One of the things that you can also do, like I said, is follow up spectroscopy of the sources you find with JWST. So we put in for a director's discretionary time program, we got a spectrum of Maisie's galaxy and we confirmed that it's actually at redshift 11.4. So we were right about this. This was pretty exciting. We got the break. So you can see the break in the spectrum here. And then it was a good time to have all of these data accepted because we were able to confirm not only the redshift of this source, but also to follow up on those 2 sources that could have been different redshifts. And we find they're actually all at redshift 4.9. So instead of redshift 16, the source was a really exciting, really interesting source with incredibly strong emission lines we didn't expect to see in a red continuum source at this redshift. So at redshift 4.9, we have these really strong emission line galaxies that mimic these high redshift sources in our modeling, but we didn't just find one, we found 4. So we actually found a new overdensity of galaxies by accident by looking at some of these sources that could have been high redshift, but were actually lower redshift sources. So it wasn't a failure, in my opinion. It was a pretty exciting discovery and a really good lesson that we learned about how we do our photometric model fitting and things like that. So this was a pretty exciting thing to be part of as well. And I also wanted to just bring this back where we had our NIRCam imaging of this redshift 10 galaxy where we had actually 2 interacting galaxies instead of just one source, which we thought was the case from Hubble. But we did put near spec on this. So we have near spec prism data. So we actually have a spectroscopic redshift. This was a pretty exciting discovery. And so we got a spectroscopic redshift. This source is actually at redshift 10.2. So we were not far off. Again, the turnover in our modeling is pretty sharp, but in reality, these turnovers are not quite so sharp. That's the discrepancy in some of our redshift measurements. But to confirm the spectroscopic redshift of this particular source or interacting pair of sources is pretty exciting as well. Then we actually followed it up in the next cycle with high resolution spectroscopy. So on the left, I'm showing high resolution spectroscopy of this source. from near spec in the 395H, and then I'm also showing MIRI. So MIRI has spectroscopy as well. So the longer wavelengths where we cannot see H alpha and we cannot see O3 from near spec because it's shifted out of the near spec wavelength coverage, we have MIRI. So we have MIRI spectroscopy of this particular source. And we were able to resolve the O2 doublet with a high resolution because of this wavelength they're separated out, which was really exciting. We could say something about the physical properties of these galaxies, say something about the star formation rate and all these other things with all this data. So now we're not just discovering, we're not just confirming, we're actually studying the detailed physical properties of these early galaxies, which is an incredibly exciting time to be doing high redshift galaxy astronomy research. I want to just shout out HCAPER's program. So this is more follow-up spectroscopy. So again, we've targeted a lot of these with imaging with NIRCam, but we want to follow up with spectroscopy. So this ends up being thousands, tens of thousands of spectra for galaxies in these extragalactic fields from the HCAPER's program. All of the observations have been completed. We're working on getting the catalog out, but we're able to discover a lot of really cool galaxies and confirm the high redshift nature of a lot of sources, but also we found cool things like AGN, as well as some other kind of extreme emission line galaxies. So stay tuned for results from the HCAPER's team for that. And one of the other things that I've been kind of trying to look into is of all of those sources I showed you before from HST, where we had all of these high redshift candidate galaxies where we had imaging and we expected them to be at high redshift. We have now followed up every single one of them with JWST in some capacity, either with imaging or with spectroscopy. And 7 out of 10 are confirmed to still be high redshift. And so actually, I think as of last month, maybe it's 8 out of 10. We got the last one and we confirmed that it's a high redshift galaxy. And so we were doing a really good job of being careful with our selection of high redshift galaxies with HST, and that we can confirm that these are high redshift sources. Of the ones that are not, so one of them was actually a transient source, and so that was actually mimicking a high redshift galaxy. It was a transient source and it's no longer observed in the JWST imaging. And then another one is actually a low redshift interloper. And so we do have some contamination from our early galaxy samples with HST, but I think we're doing a pretty good job. And here I'm just showing you some of those spectroscopically confirmed sources. So here's all of the spectroscopically confirmed galaxies in these HST samples. And here at the bottom is this GNZ11. And then here's that redshift 8.7 source that we talked about before. And so we're getting really cool spectroscopy of everything and confirmations. And so we're being able to study these galaxies, not just individually, but kind of in context now that we have a larger sample size that we have detailed spectroscopy for. And it turns out that not only were these 2 particular sources at redshift 8.6, 8.7 from the Keck data, which I had had this discovery of this overdensity, but there are 13 spectroscopically confirmed redshift 8.7 sources in the Sears field in EGS at the same redshift. And so we have a pretty strong overdensity of galaxies, which explains why we see Lyman alpha emission from a lot of them, which is pretty exciting. One of the other really interesting things is we're finding a lot of galaxies that have surprising AGN. And so one of the things that we followed up, like I said before, was these galaxies trying to understand their physical properties and also to get more detailed spectroscopy of them past just the Lyman alpha emission. And in one particular case, what we found in this source at redshift 6.8 is that at 8.7 is that we found a broad component in the H beta line. And so we interpreted this as being an AGN, which means that the actual material around the AGN at the center of the galaxy, the active galactic nucleus, or the massive black hole that's actively accreting, is moving this material a lot faster. And so not only are we seeing a broadened emission line, but we're actually able to determine that this source seems to have no X-ray emission that would correspond with an AGN. It didn't have any submillimeter emission that maybe corresponded with an AGN, but in combination with some of the emission lines with this broad feature and all these other details, we interpreted this spectroscopy as being coming from an AGN. And at the time, it was the highest redshift galaxy, which is our highest redshift AGN, I'm sorry, which was pretty exciting. And so this was a NASA press release that came out about this paper where here's Sears 1019 over here, just to try to showcase, like, here's where all the other AGN are that were discovered by other telescopes. We had a couple other fainter AGN that were discovered in the Sears program, which was pretty exciting, which is in a regime that was really difficult to do prior to JWST because they were so faint. We needed the sensitivity of JWST to find. But this galaxy might seem like the black hole here, the black hole mass is on the y-axis here. It might seem like it's a small black hole, but it's pretty large for the time that it was made. And so this was one of the other surprising results coming out of GWST, is that a lot of these galaxies that had AGN in them were measuring black hole masses for these AGN that were quite high. And so we could not figure out the best way or how they made a black hole so big so soon. So at the bottom, we have redshift, and then we have black hole mass on the y-axis. And so in order to make a massive black hole at this size this early, we would need something exotic in any kind of way. We would need a big POP3 star to have exploded and then accreted at super Eddington accretion multiple times, or we would have to have a dense star cluster that collapsed into a black hole, so multiple stars actually coming all together to make a black hole, or we'd have to have a direct collapse black hole that also grew pretty quickly. And so this was all of the quasars that were discovered prior to GWST, which we also could not explain the mass of the black holes in these quasars at redshift 7, 7.5. And so we were already confused about how we got here, and there was no data points. And so we got to put the first kind of data point on this plot, which was pretty exciting. Even more exciting, in my opinion, is how many more data points have been added to this figure since then. And so in fact, GNZ11 is actually sitting right here. So GNZ11 has indications of AGN activity potentially, as well as several other sources. And I would like to highlight that the redshift 10 line is about right here. So there are 3 sources above redshift 10 that have potential AGN and black holes that are so big that we don't know how that they were made that early. So this is a really exciting time to be studying early galaxies and how they grew their black holes. Stay tuned for a lot more results coming out about these. One of the ways that was potentially how we were able to explain these massive black holes was through super Eddington accretion. So this is a paper led by Irini Lambrides using some of the JADES data, where we were showing that super Eddington accretion would be intrinsically X-ray weak, and you would also not see some of these emission line features in the rest frame UV. And so we looked at the JADE spectroscopy of these early AGN at these higher redshifts, and we were finding that it looks like it's possible that super Eddington accretion could explain some of the sizes of these black holes from these data. One of the other things that we were trying to do is to study the detailed galaxy properties. And I've shown you a lot of spectroscopy that was an hour or less than an hour of observation time, but now we've spectroscopically confirmed a lot of sources. We want to go deeper. We want to study the more detailed physical properties of these galaxies, and that's where the THRILLS program comes in. This is the high redshift and ionization line search program that Taylor Hutchison and I are PIs of. So this was 2 pointings with near spec G395M at over almost 9 hours depth in each pointing. And so with the spectroscopy we're showing here at the bottom, the Sears spectrum of this source is in the light blue, and you can see that we do detect quite a few emission lines in the Sears spectrum, but what we're able to do with the actual, you can zoom in here, the dark spectrum is the THRILL spectrum. So this is versus an hour of exposure time versus 8 to 9 hours of exposure time. You're able to detect fainter lines like the helium line here. And here's another example of Ruby spectrum, which is also about an hour, where you're able to detect things like the sulfur 2 line and actually get the broad H alpha plus the nitrogen 2 emission line features, and you're able to detect some sulfur 3 and other things that we were not able to see in the shallower data. And so this program, our paper came out on this program, but also one of the things that we did with this was combine forces with the C3PO program, which is the carbon 3 plus oxygen, which is PI'd by Casey Papovich, Wada Hu, and Taylor Hutchison. And so we have 2 pointings from C3PO as well, with over 10 hours in the 395M and 13 hours in the 140. And a lot of these sources overlapped. In fact, one of the things that we really wanted to study was Maisie's galaxy. So this was one of the early galaxies we found. It's at a redshift of 11.4, and we wanted to study it in more detail. So we do have a spectroscopic redshift from PRISM data from the break and from an O2 emission line, but we wanted to study it in more detail. So now in combination with these 2 programs, we have over 19 hours of exposure time on Maisie's galaxy, and we're able to see the oxygen 2 line along with this neon 3 and this helium 1 line. Now, you might think that's not quite all that many emission lines, and it's really not. In fact, compared to some of these other early galaxies, even these galaxies at redshift 10 and greater that we have spectroscopy of, Maisie's galaxy doesn't seem to have any kind of extreme emission line features or surprising emission lines. It just has O2, neon 3, and helium 1. So what can we do with that information? Well, due to the redshift and the resolution of our spectroscopy, we can kind of put some constraints on the O2 doublet ratio, which helps us do things like measure the electron density. And so what we are able to do with that is assume an electron temperature. And here we're using the same electron temperature that was measured directly from the most closest in redshift, which is this MAXO 647 JD, which is that pair of sources I've been showing you spectroscopy of where we had the resolved O2. And so Maisie's galaxy lies here. And so here are other detections for electron density as a function of redshift, where we have oxygen 2 and carbon 3 resolved doublets, and sulfur 2 as well, or even line ratios with O3. And so what we're able to do is put data points on this plot, which is pretty exciting, and see how this potential relationship evolves across redshift. And so this has been postulated that this electron density evolves as a function of 1 plus 0 1 plus c squared. So I'm showing that shaded here. And there are large error bars on a lot of these early galaxies. Again, it's difficult to do this, even these redshifts. We went from the difficult thing to do with HST and Keck to the difficult thing to do with JWST. And so we can put some constraints on the electron density for these early galaxies, as well as some other things. But I just want to highlight some other science that came out of the Thrills program. And so this is actually an LRD, which I haven't talked about at all. But these are little red dots, which seem to be all over our JWST images and are surprising little potential AGN early on in the universe that are quite confusing and quite prominent in a lot of our imaging. And so this particular one is originally found in the Rubies program. And so this is the prism spectrum where you see this sharp break. You see this V shape that's indicative of the LRDs. But we also have 8 hours of spectroscopy, and you see some really exciting things like iron. So there's a lot of iron emission in this galaxy, and that gives you a lot of information about the size of the black hole, the accretion area, and the actual physical structure of these particular sources. So this is a pretty exciting result to come out of the Thrills data. One other thing that's coming out of Thrills and is being worked on by Issa Cox is a pair of merging galaxies. So this is at redshift 6. We have this pair of sources that we thought were individual sources when we originally did this. And so we only had the one targeted source here, but we were actually able to see two individual traces in our near spec spectrum. So this is one of the sources, and then this is the other source. And so you're able to actually resolve out the two sources, and they have different emission line properties and different star formation rates and metallicities, but they seem to be a merging pair of galaxies early on in the early universe. And so there's some pretty exciting science that we're able to do with this deep spectroscopy, and I just wanted to shout those out. One of the other things that we have coming up that I'm excited about is this program called SPAM, which I promise is an acronym that makes sense, but is a little bit tortured. So we're just going to consider it SPAM, and we're adding medium band observations to the SEERS program. So like I showed you before, we had NIRCam imaging from SEERS, and so we had all of these filters here in teal from the SEERS program, but we're actually adding 10 more photometric bands. And so we're adding all of the medium bands, with the exception of like 2, to the SEERS observation, which allows us to do a lot of really cool science, including things like measuring overdensities, ruling out these high redshift, low redshift interlopers with the additional data. And here we're showing a couple different spectra of galaxies just to show you where the emission lines would fall and how those would look different in the different filters that we have observations. So this is coming up. This data will be out in June. This is PI'd by Kelsey Davis and I. And please stay tuned for a lot of the really cool results that the medium bands are going to be adding. And I will just say one more thing that we're also excited about Roman coming up. So not only do we have a lot of really detailed galaxy studies with JWST at the high redshift, but we're also going to be able to study galaxies in context because we'll have the numbers with the Roman telescope. So just here in the center, this is a picture I like to show where just in the center, the white square is showing you the field of view of Hubble and JWST, and with one individual exposure of Roman is the blue. So we are going to be able to get bunch more galaxies at the early universe and be able to study galaxies much more in context and see the bigger picture of the early universe. So I will stop there and we can do discussion.
Thank you for the nice talk. Where's the reaction emoji? Right there. Great. So let's take questions from the room. Feel free to raise your hand. I can monitor hands. Don't be shy. Anyone? Question for Rebecca? Jason, go for it.
Yeah, that was really interesting to listen to everything you're working on. You covered a lot of ground. My question actually goes back to one of the earlier bits you were talking about, where you were saying that you were working on improved templates, spectral templates for high redshift galaxies,
Mhm.
and I'm really curious about what is the biggest like physical difference that impacts the template. Is it metallicity or is it um, I don't know, binarity?
So we did use binaries in this particular set of templates, but I think what's potentially the most different is that we have low metallicities, we have high ionization parameters, and we have really young ages. And so we have younger stars. So I think the blue slope here, that's the most drastic difference you can see is the slope of these particular spectrum is coming from the abundance of the younger stars and the younger stellar populations and lack of older stellar populations because not a lot of time has passed. So I think the biggest difference is in the slope. There's a lot of differences in the emission line features and things like that. We took out Lyman alpha, for example, right? So there's no Lyman alpha in these early galaxies that is detectable. So, right, so they are emitting it, but it is probably not going to be detected. That being said, there has been Lyman alpha detected at redshift 13 with JWST, which I didn't quite go over, but there are a few exceptions to these cases. But in a large part, I think it's the younger stellar population and the binary stars that are making the bigger difference.
Can I ask one follow-up question that kind of gets into the weeds a little bit?
Sure.
You said the ionization parameter, you dialed it up a little bit higher than you might normally. How high are we talking?
Well, if I may, I have measured the ionization parameter for some of these redshift 10 and greater sources, and it's about a minus 2.6. Um, And so I don't know what the limit of the ionization parameter was for these particular templates. I mean, it's in the paper.
Sure.
I could
Yeah.
definitely look that up for you. Um, but we we added nebular continuum on top of that. And so we also had a couple different things that were going on in the templates that kind of all contributed. But I do think we got to beta slopes that were like minus 2 or 3. I can't remember exactly the numbers off the top of my head, but um, yeah, we dialed it up pretty.
Yeah. Well, thanks a lot. And very fascinating talk.
Thank you.
I think Mike has a follow-up question. Mike, you want to go ahead and ask that?
Hi, not sure if you can hear me, can you?
Yes.
Oh, great. Okay. So I wanted to ask about metallicities. Are you able to quantify any of the metallicities in your spectra? As you go back to redshift 10, are you seeing Z as high as solar or close to solar? Or conversely, are you seeing any galaxies that seem to be pretty primordial, 10 minus, say, 10 minus 4 or so? What are the extremes that you're seeing in your high redshift galaxies?
So I'm glad you asked because I do have that. If I can get back to where I
So I
was.
can submit my invoice to you. Okay, good.
So here I'm showing the metallicity that we've measured from neon 3 over O2, which is we can use this relationship that's been kind of calibrated at higher redshifts from this paper here. And we also have metallicities from SED fitting. And so if we look at Maisie's galaxy in the neon 3 over O2 ratio, we get a metallicity from that. It's a little bit less than if we use the SED fitting. With SED fitting, we're getting like 22% solar, and with the neon 3 over O2, we're getting like 17% solar, 15, 16% solar. Some of these are down to the 5% solar that we've been able to measure. And now when you get to the really low metallicities, like you're talking 10 to the minus 4, things like that, that we would probably need for these direct collapse black holes to be the right answer.
Mhm.
we don't have the sensitivity yet or the depth achieved to do those measurements, those metallicity measurements. And especially at these redshifts, you really need like the Muri data to get the O3 emission line, and things like that. And so we're limited a bit by the depth of the data that exists so far. We have a lot of upcoming observations that are deeper spectroscopy of these sources, right? The first thing you do is you take a picture, you find the galaxy, you get the low resolution spectra to get the redshift, then you get higher resolution, deeper spectroscopy to study the details. And so I think we're in that third stage of studying these early galaxies. And so I think there's going to be a lot more coming out of these more recent and upcoming programs with JWST that are going deep enough to do these measurements.
But do I understand that it's not a limit of JWST, it's just that you haven't had enough telescope time yet? So if instead of looking at an object for twiddle 10 hours, you look for twiddle 100 hours, you might well be able to say, yep, this guy is 10 minus 4 instead of 10 minus 3 in metallicity.
Could you
Terrific.
Be back?
I would give you the time. I mean, I think that's incredibly important. You've obviously got to pick the low-hanging fruit, which is what you're doing now. But finding even a couple of these guys or pushing below 10 minus 4 is clearly incredibly important. So you get my vote.
Thank you.
Go ahead, John.
Hey, Rebecca, great talk. Really enjoyed this. So we're looking at the high redshift universe. We're looking at redshift 10. How concerned should we be about population demographics and generalizing these sort of crazy bright sources at these early times to a more general population at these early, high redshifts?
Yeah, so I'm glad you asked that because it's kind of what the gist of my paper that I'm almost done with is that we have a lot of these sources that we've studied at redshift. I'm going to start with redshift greater than 10 because that's what I've been focusing on lately, where we have some extreme systems. We have the crazy stuff, the bright stuff. The first things you see are going to be the wild, wacky things. They're really bright, they're really extreme, the crazy emission lines, things like GNZ11 and now some of these other sources that have surprising features. And I would like to argue that Maisie's galaxy is not that. It's very blue. It's bright enough for us to have seen, but it's not actively star forming. In fact, if you look at the star formation rate from O2, which take all of the caveats from that, and you look at the other O2 emission line star formation rates that you can calculate from all the other redshift greater than 10 sources, it's pretty low. Like it's possible that it just went through a burst and is in a lull. We think these galaxies are kind of bursty, and so some of these ones that we're seeing are probably really active, doing crazy, exciting things, and those are the ones that we can see the easiest. And so we need to hammer down in these 19-hour exposure times into these deeper depths to get some of the more typical galaxy population. I think we have, as at my last count from the literature, we have spectroscopically confirmed over 44 galaxies at redshift greater than 10, but only a handful of those sources have Muri observations where we can get H alpha and we can get O3, or only a handful of those have long exposure times where we can study them in any kind of detail. And so I think what we really need is like I keep saying, is more exposure time on these interesting sources to understand the galaxies in context and in the total population instead of just studying the really extreme, crazy things.
Thanks.
Mm-hmm.
Thank you for the question. So Benny, I see that you unmuted yourself.
No, I'm just trying to, if I start squawking, that somebody can hear. No, I mean, one of the questions was like, yeah, how big are the samples? And you just answered that. Because I was curious about the metallicity. Do you also see, I mean, I know Ryan saw a very odd sort of Balmer decrement, so that there's some evidence of really strange ISM conditions, and not just the electron density, but also because you've got some heavy elements in there. Some of it has coalesced, some of it is not. Dust must be very odd. Do you see some evidence of like a strange attenuation curve? This is my probably horse.
It's a great question. It's a little difficult to say because there are, to my knowledge, 3 sources with Muri observations with an H alpha detections above redshift 10. And oftentimes there's no detected H beta, it's too faint. Maybe we have from near spec some H gamma, some H delta, but doing the Balmer decrements at these redshifts is very difficult without the deeper data. And there's only a handful handful of sources that have that, and how well we believe the calibration between NIRSpec and MIRI being one of the other caveats that we got to kind of throw in there. So yes, I think at the slightly lower redshift, we're seeing some interesting Balmer decrements when you can actually see the H alpha, H beta, but with NIRSpec alone, I think it's still unknown as of right now at these high redshifts. Yeah, but I think it's important that we get MIRI data for them. So if the TAC would accept those proposals too, that'd be great.
Great. Any other questions? Don't be shy. Going one, going twice.
Is case B still okay?
I think we
that
still
sounds
largely assume it because I don't think we have a different answer as of now.
Can I popcorn on that question? So I remember in the early days there was some alarming differences between stellar AV and like nebular-based AV from Balmer decrements. Has that held up? I mean, maybe redshift greater than 10 is not the place to be looking for this, but has there been any sort of consensus that yes, we're just looking at different sight lines, or sort of what has been the evolution of that conversation from what you've seen?
I'm not the best person to talk about that. That's not really my expertise, but it's my understanding that we are still having weird Balmer decrements.
Okay.
That it's still an ongoing issue, if we should call it that. Yeah.
Okay, good. That's what I'm seeing as well. So that's all consistent.
Okay, good. At least we agree that everything's weird.
Yeah, I think we've just sort of accepted at this point where okay,
I
that's
don't
what the
know.
data
I don't know how
is.
to do a Balmer decrement. It doesn't make sense. Yeah.
Okay, cool.
Mm-hmm.
I see there's a raised 10 from Maria.
I think it's a good last question, maybe from my daughter. You want to ask?
How'd you go to space? How? You got to do a lot of work. And you got to work really hard in school, and then you got to apply to be an astronaut, and then you got to go through training for a while, and then hopefully you get to go to space. But I think there's a lot of really cool people that get to do things like that. So if that's something you want to do, I believe in you.
Thank you.
Mm-hmm.
Great. Well, that's a good note to end on. So thank you all for joining us. And we will have our last seminar of the school year in 4 weeks. So again, if you're interested in giving a talk next year, do reach out to Benny or John or me if you want to, and we can arrange that. All right, I'll see you all back in 4 weeks. Bye.
Super interesting. Thanks, Rebecca.
Thank you.